Today's video is going to tie up some loose ends for standard 9 in terms of the coordinate proofs that we've been working on. So as we've gone through this standard, we've learned about coordinate proofs one shape at a time. So first we focused on showing that something was a rhombus, and then showing that it was a rectangle, and then showing that it was a square. However, when it comes to your assessment, the instructions are going to change a little bit, and so we wanted to do a quick overview of what that official final proof should look like based on knowing all of the coordinate proof techniques now instead of only some of them. So we're going to start the same way that we have been by going ahead and labeling those points on our graph, and we always want to be careful to pay attention to the official name that they're giving us for the quadrilateral to make sure that we're graphing it correctly. So if we're going to graph P, we're going to go 5 boxes to the left and 4 boxes up. For M, 1 to the right and 8 up. T is going to be 3 to the right and 5 up. And then S, 3 to the left and 1 up. Connecting in the order of the name, we're going to connect from P to M, then to T, then to S, and back to P to make it a polygon. Now you can look at that shape and you can say, I think that looks like a rectangle. But the idea is that we're classifying the quadrilateral with the most specific name possible, and this is the key, providing all algebraic evidence for your classification. So that means we include details about both what the shape is and how we know that algebraically, but also what the shape is not and how we know that algebraically. So I'm going to be very specific in the way that I'm showing my work. This work matches for every single one of these proofs. It's just a matter of how you use those values that you find to make your conclusion. So just like with standard 8, we're going to start by thinking about our slopes. And I'm going to focus on opposite sides because showing that the shape is a parallelogram is always our first priority. So starting with segment PM, you can find your slope using the slope formula with x1, y1, x2, y2, or you can find your slope by counting rise over run. The rise for this one is +4 and the run is +6. We are going to reduce that slope so that we can make a clear, accurate conclusion about our opposite sides being parallel. Segment ST would be the opposite side. Again, the rise is 4 and the run is 6. And so that slope is also 2/3. The key is to make sure that you make a conclusion. So these two equal slopes tell us that segment PM is parallel to segment ST. So we're being really obvious about what those algebraic numbers tell us in terms of the geometry. In order to be a parallelogram, we can't just have opposite sides parallel. We need the second set of opposite sides to be parallel as well. So I'm going to come back for segment PS next. That has a rise of -3 and a run of +2 since we're moving to the right. And that cannot be reduced. So I move over to the opposite side, segment MT. That slope has a rise again of -3 and a run of +2. So I can compare those two slopes and make a conclusion that segment PS is parallel to segment MT. Now before we go any farther, let's actually write down what that tells us. At this stage, if we have two sets of opposite sides parallel, we are to the point where we can say we know this quadrilateral is a parallelogram. That's good news because that means I'm ready to continue on with my coordinate proof. If I hadn't ended up with a parallelogram, this process would be done and we would just say that PMTS is a quadrilateral, but it wasn't a special quadrilateral. Continuing on, I think the next best thing to do is to look at two consecutive sides to see if I also have a right angle, which will make this a rectangle. I typically look at my two sides in the middle because if we're looking at those middle sides, they're always guaranteed to intersect at a corner. So if I'm looking at 2/3 and -3/2, we need those to be both opposite and reciprocal slopes in order for these two segments to be perpendicular to create a right angle. A way that you can check for that is by multiplying them together. If you multiply straight across, the fraction has to simplify to be -1 in order for us to be able to make our conclusion. Now, not all teachers require that work to be shown, but that is a way that you can show that you have perpendicular segments. As long as you can identify that they're both opposite and reciprocal, we're able to make this conclusion. So if we're in a situation where we have a parallelogram and we know that some consecutive sides are perpendicular, now we're able to make the conclusion that that parallelogram is special, and that right angle makes it so that we're dealing with a rectangle. Our next stage is to figure out if we're also dealing with a rhombus. So for a rhombus, I'm going to focus on those same two sides. However, I'm not interested in their slopes anymore. In order for a parallelogram to be a rhombus, we need to show that those two sides are congruent. They have the same distance. Now, it's pretty obvious from this graph that they are not the same distance, but I need the algebraic evidence. So I need to find the distances in order to show that they are not equal. Now, the official distance formula says that I need to take my x2, which if I'm focusing on S and T, I could go ahead and label these x1, y1, x2, y2. The official distance formula says to take your x2, which is -3, subtract your x1, which is +3, square that, and then add onto it y2, which is 1, minus y1, which is 5. That part gets squared as well. Simplifying inside those parentheses gives us a -6 that needs to be squared and a -4 that needs to be squared. That ends up being 36 plus 16, which is 52. So if you're using the official full-fledged distance formula and going back to the points, that's what it would look like. But remember, the first portion of the distance formula is the difference between the x values, and that's the same as the run in your slope. So you can also look at your unreduced slope. So like for ST, that was 6, and that ends up being the same value when you square it. And then your rise is your difference in your y values, and so that can get plugged in here, and then you'll square it to get the same answer. So if we use that method for segment PS, the difference in the x's was 2, that's the run, and then the difference in the y's was -3, that's the rise. So this slope, or not slope, excuse me, this distance turns out to be 4 squared plus 9, 4 plus 9, which is 16. That tells me, if I compare these two distances, that segment ST is in fact not congruent to segment PS. And so my conclusion from that piece of algebraic work is that this is not a rhombus. So if I'm looking for the most specific name for quadrilateral PMTS, it was a parallelogram and it was a rectangle, but it wasn't a rhombus. That means that rectangle is the most specific name that I can give to that quadrilateral. Okay, go ahead and pause the video, try to work through that process for number 2. I will be back in a moment with some information that you can check your answer with to make sure that you are on the right track and have all the evidence shown as you need it to be. Okay, I'm going to walk you through the highlights for this one. There is something interesting happening here. When you graph these points, G, L, M, and H, we're actually told to connect them in an order that's different than they were listed in. So just be careful that once you get G, L, M, and H graphed, you're actually connecting G to H to L, L to M, and then closing it up to make that into a polygon. I've got my slope set up here. I started with GM, so find that in your list wherever you had it written down. That slope was 2/3. Both were positive. I went to the opposite side HL next. That slope is also 2/3. So I'm able to say that segment GM is parallel to segment HL. Next up was GH. That slope was -5/3. Since I was going down and right, one of those directions was negative. And then for ML, that same -5/3 slope occurred. So segment GH is parallel to segment ML. Those two facts combine together to tell me I'm dealing with a parallelogram. Because I got a yes for parallelogram, I'm going to compare two consecutive sides and their slopes. So I'm looking at 2/3 and -5/3. If we were to actually multiply those across, we'd get -10/9. -10/9 is not equal to -1. So that means that these segments this time are not perpendicular, which means we do not have a rectangle. Honestly, that was a little surprising to me because this definitely looked rectangle-y to me, but the math doesn't work out, so it must be really close to right angles, but not exactly right angles. Continuing on, I need to decide if this is a rhombus or not. And so I'm looking at the same two consecutive sides. You don't have to do that, but I like to just be consistent between my rectangle test and my rhombus test. The distance between H and L should turn out to be √13, and the distance between G and H is √34. That to me was not as surprising, because if I'm looking at the distance between H and L, it does look much shorter than the distance between G and H. So I was not expecting them to be congruent, but this is my algebraic evidence for why HL is not congruent to GH. So this shape is also not a rhombus. So if it is a parallelogram, but it's not a rectangle, and it's not a rhombus, then that means the best that I can do is make a conclusion that GHLM is a parallelogram. All right, go ahead and flip it over to the back. You've got two more problems back there that you can try. Go ahead and pause if you would like to take care of those and be able to check your work once you're done. I'll be back with the answers in just a minute. All right, welcome back. It looks like we have the same situation happening in this problem as the last one. The name of the quadrilateral is ABCD, but that's not the order that the points are given to us in. So when you graph ADCB, be careful. You could actually still create this quadrilateral if you connected them in that order, but officially A connects to B, and then to C, and then to D to make sure that you're making the quadrilateral that they're asking you to investigate. I started with side AB, so find wherever that is in your list of slopes. AB has a slope of -5/-3, but a negative divided by a negative simplifies to be positive. The opposite side, DC, is the same. The slope is -5/-3, but that simplifies to be a positive 5/3. Those two slopes match, so that means we know segment AB is parallel to segment DC. Continuing on, segment AD was the next one that I chose. That slope is -3 for going down, but then +5 as we run to the right. Segment BC does the exact same thing, so those slopes are both -3/5, which means segment AD is parallel to segment BC, and those two facts combine together to tell me I'm dealing with a parallelogram. Continuing on, I'm going to pick two consecutive sides, so I focused on the sides that connected at point D. So over here in the picture, I'm trying to determine if this is a right angle or not. The first slope I had was 5/3. The next slope was -3/5, You can investigate whether those are opposite reciprocals or multiply to get negative 15 over positive 15, which is in fact equal to negative 1. And so that means yes, segment DC is perpendicular to segment AD, or D is a right angle, which means we're dealing with a rectangle. Next up, to investigate whether or not this is also a rhombus, I need to focus on two consecutive sides again. So I stuck with DC and AD, but this time I'm looking for their lengths. So that distance formula tells me to subtract the x values. When you do that, you get 3. Square that and add it to the y value subtracted, which is 5. So that distance turned out to be the square root of 34. And when I went through the process for AD, the same exact value, square root of 34, was the distance. If these two lengths are the same, that means segment DC is congruent to segment AD, and that tells me I'm dealing with a rhombus. So when you have a quadrilateral that is a parallelogram, and it's a rectangle, and it's a rhombus, that's when we officially get to call it a square. So our final conclusion on this one is that ABCD is a square. If you'd like to try the next one on your own and then double check your work, go ahead and pause the video. This one has the same situation happening where the name of the quadrilateral does not match the order of the points as they were given. So once we have our Z, W, X, and Y graphed and labeled, we want to make sure that we connect X to W, W to Y, and Y back to Z before closing up that shape. My first slope was segment YW. That was a rise of 1 and a run of 4 to the right, so positive 1/4. ZX had that exact same slope of 1/4, so segment YW is parallel to segment ZX. The other two sides, YZ and WX, we had a rise of -4 and a run of -1. Negative divided by negative simplifies to be positive, and segment WX had the exact same slope. Negative divided by a negative still simplified to be a positive. So segment YZ was parallel to segment WX. Those two combine together to tell us we do have a parallelogram for the fourth and final time today. Taking a look at some consecutive sides to see about that right angle that should happen if they're perpendicular, I'm looking at ZX and YZ, so I'm investigating angle Z right there. Doesn't seem like a right angle, but if I'm comparing my slopes, 1/4 and 4/1 are reciprocals, but they are not opposites. So if you multiply those, you'll get positive 4 over positive 4, which is positive 1. In order for them to be opposite reciprocals, it needs to multiply to be -1. So that means that segment ZX is not perpendicular to segment YZ. There's no right angle there, which means it's not a rectangle. Continuing on to the last part, we need to test for whether or not this is a rhombus. So I'm going to stick with segment ZX and segment YZ, but I'm looking for length this time. So the difference in my x's, which is also the same thing as my run for ZX, was 4. 4 squared plus the difference in the y's, or the rise squared, was 1. 4 squared plus 1 squared is 17. And when we repeat that process for segment YZ, it gives us the exact same values. Our unreduced slope has the difference in the x's as -1 and the difference in the y's as -4. But a negative squared is still a positive, so we still get positive square root of 17, which means that segment ZX is congruent to segment YZ, and we do then have evidence that this shape is a rhombus. So if we go back through and we look, we have a parallelogram that is not a rectangle, but is a rhombus. So our final conclusion should be that XWYZ is a rhombus. That's the most specific name we can give. So the only option we didn't cover on this page is what would happen if you ended up with something that was not parallel. If you ended up with something that was not parallel, you wouldn't continue the process. you would just say that the quadrilateral is not a parallelogram, and if it's not a parallelogram, it can't be a rectangle or a rhombus or a square. Hopefully that helps you to kind of gather up all the different coordinate proofs and see what it will look like on your assessment. Thanks for watching.